we now want to dive a little bit more into the mathematics of waves. Okay, so with this math background, hopefully, even though we're going to go a little slight on some of the derivations, we will at least give you the most important results. Okay, but first things first. So once again, we have our wave, and I'm gonna let's make this explicitly a function of position and time. Okay, even though it will be on the right side, it's never a bad thing to explicitly state what your function is a function of. So we have our amplitude times sine times kx minus omega t. So this is assuming our phase constant is 0. Okay. So first things first, what is the velocity of the wave? Well, the velocity is the derivative with respect to time. So if I take the derivative of this, I'm going to get a, and we get cosine of kx minus omega t. And when we take the derivative of the argument, we get a minus omega. It's a really funky looking omega. There we go. So this becomes minus a times omega cosine kx minus omega t. Okay? So, that was a magnet falling off of my refrigerator. Apologies if it startled you. So oh man, I can do better than that. Okay, so here is our y function. Y of x and t. Whereas my velocity function is a minus cosine of this. Okay, so remember your velocity is the rate at which your position is changing. Okay, but because our wave is moving forward, we have this minus sign attached to our omega. And so the result is that this starts, if I plug in 0 for t and 0 for x, then this starts down here. Okay? And let's draw some lines here that represent our maximum and 0 positions. So when the wave gets to this point in position space, it is at the maximum, it's at the amplitude. Here, it's at 0. Here, it's at the negative amplitude. Here, it's at 0. If my drawing were perfect, all of these would be evenly spaced, so use your imagination. Okay? All right. So my wave, the velocity of my wave, starts here, and the derivative at your extrema is 0, so my wave has to be 0 at this point. The velocity of my wave has to be 0 at this point. And when it goes through your equilibrium position, that's when it has its maximum slope, and so it will be like this. So this is a negative slope, but because of this negative sign, that makes it a positive value. So if I were to plot my velocity as a function of time, it would essentially look like this. Okay? So wherever it crosses the x-axis on its way up or down, that is when your velocity will be the highest. And that is, well, switched sign, right? Because of this minus sign, okay? And when your position is at a maximum displacement, whether it's a crest or a trough, those are your zeros on your velocity graph because these have 0 slope and your velocity is your slope, so those represent your zeros, okay? So if I compare this equation to this form, so let's look at this equation compared to this form. Now, yes, one is a cosine, the other is a sine, but they're both sinusoidal, and they're only shifted by a 90-degree phase constant. So mathematically, they will have the same period, they'll have the same wavelength, and so forth, all right? But the only thing that really is different here is that your amplitude for your position is A, whereas your amplitude for your velocity, or your Vmax, so this would be negative Vmax, and this would be positive Vmax, okay, is now given by your amplitude in position space times your angular frequency. Okay, so that represents the maximum velocity of the particles as they're moving up and down. Now, this is not the velocity of the wave. This is the velocity of your medium. I really should have said that before. Okay, so this is the velocity of the medium. So this would be like the water molecules that are bouncing up and down. The wave itself is traveling through the water, but the water molecules are bouncing up and down. And the maximum speed that they're going to do that with is equal to the amplitude, the spatial amplitude times your angular frequency. Okay? So what about the acceleration? So A is equal to dv dt, right? So this is going to be the time derivative of negative A omega cosine kx minus omega t. So I need to take the time derivative of that entire expression. Well, A and omega are constants, so they stay. The derivative of cosine is negative sine. And the derivative of the argument is negative omega again. So we get negative A omega squared sine kx minus omega t. Okay? And so once again, your maximum acceleration of your medium is equal to a times omega squared. All right. And if we look at the plots once again, okay, so my velocity as a function of position looks like this, and my acceleration if we do the same thing, right? Look at your special points where cosine is 0, sine will be a maximum, and where cosine is a maximum, sine will be 0. And so shape-wise, this is just an inverted sine function, right? So minus a omega squared sine kx minus omega t. So I'm going to start out at 0, and when my velocity is 0, my acceleration will be maximized. And then when my velocity is maximized, my acceleration will be 0. And I will have this. Okay. Did we get all of our special point? Oh, I missed one. That's why it looks weird. Yeah, we missed this one. Yeah. So yeah, it's going to look a little funky because my artwork isn't great, but it will be maximized, go to 0, go to maximum, 0, and then maximum again. That looks really bad, but if we don't try to stick with all of those weird lines, it just looks like a negative sine function. Okay. And again, it'll have the same period as, it'll have the same wavelength, frequency, period, angular frequency, all those things. So it has the same wave number and angular frequency as your original spatial wave. Okay, and so if you think about it, this should make a little bit of sense. So let's actually also draw y of x up here. So y of x was originally just your regular sine function. Okay, so when your position function is moving upward, your acceleration is in the opposite direction. Okay. And if you think about it, that should make some sense. Okay. And we'll draw an analogy here in a minute, and hopefully it will make sense if it doesn't yet. Okay. But so when I start moving up that direction, my acceleration is in this direction. Okay. And then my maximum acceleration occurs when the displacement is maximized, but my acceleration is negative in this case. And then when my position function is 0, my acceleration is 0. Now let's start there, okay? When my position function is 0, my acceleration is 0, and that's when you're moving through the equilibrium position, and that's when the net force acting on your mass is 0. So it should make some sense that that's true, okay? And if I have a wave that's oscillating up and down like this, okay, think of a mass hanging from a spring, okay? Think of a mass hanging from a spring, and then you pull this down and you set it into motion, and it has oscillations up and down, and you track it through time and you get this kind of wave, okay? When the mass is physically on its way up, the spring is trying to push it down. Because remember, the restoring force always acts toward equilibrium. So the spring is trying to push the mass down. It's just the mass has too much inertia. So the spring can't immediately push it down. But when the spring is, or when the mass is moving upward, the spring is trying to push it down when it's on the positive side of the equilibrium position, right? And then when it reaches the peak, that is when the rate at which your velocity is changing is the greatest. Because you're at a turning point, your velocity is changing very rapidly from one direction to the other. So your acceleration is going to be maximized right at that peak when the mass is right here in its cycle, or when the mass is right here in its cycle. Now, what direction is the acceleration pointing? Well, the acceleration at this endpoint is pointing down, even though your displacement immediately before reaching the endpoint and the endpoint itself is up. Your displacement is up. Hence, your position is positive. Your acceleration is pushing the mass down. Hence why your acceleration is negative, right? And then when the mass hits the equilibrium position again, the net force goes away. So your acceleration is zero. And then when the mass is down here, the spring is trying to push it up, even though the displacements are downward. So your displacement is down, but your acceleration is trying to push it upward. And so this is why your acceleration and your positions are flip-flopped with this minus sign. Okay. And your maximum acceleration occurs right here. Okay. Now, we're not going to go through the derivation of this, but we are going to do an example to kind of pseudo justify it. Okay. So what we're going to write down is known as the wave equation. And any equation, any function that satisfies this formula is a type of wave. Okay? Now, if you do any sort of audio processing, okay, at high levels, then you may have heard of things called sawtooth waves or what's the other wave, major wave I'm thinking of? Golly gee. The name is escaping me, but it looks like this, where you just have a positive signal and then it immediately drops, and you have these kinds of things. Okay. Your sawtooth wave would look like this. So neither of these are, simple sine waves. Okay, but you can get various types of wave forms by the combination of adding multiple sine waves. Okay, now we're not going to go through all of that theory, but the whole point here is that there are multiple functions that you can have that satisfy the equation we're going to write down, this so-called wave equation. So if any function If any function satisfies this equation, it is a wave. And the equation looks like this. Okay? So this is what's known as a partial differential equation. And since the derivatives are order 2, this is a second order. Now, we're not going to go through the justification of why this wave equation works, okay? But the entire idea, the basic idea behind it is this, okay? If the rate of change of velocity equals, I'm sorry, not the rate of change of velocity. If the rate of change of your y derivative with respect to your x derivative, if the rate of change of that equals the rate of change with respect to time, okay? Now, let's break this statement down because this is a wordy statement, okay? If the rate of change of your spatial derivative, so I take now, okay, so this symbol right here is a partial derivative. And what a partial derivative does, let's get rid of our square wave. That's what I was trying to think of. It's the square wave. D dx, or partial x, means take the derivative of x and hold everything else constant. And partial t means same thing. Take derivative of t and hold everything else constant. Okay? So take your derivative of x if you have d dx, and it doesn't matter if we call it d dx or partial x. For our purposes here, they'll mean the same thing. Okay, so this kind of funky script looking d is just a new way of taking a derivative, or a way of thinking about a derivative, I really should say, because the way of taking the derivative doesn't change. You take the derivative with respect to the specified variable, just holding everything else constant. Okay, now, so if the rate of change of dy dx, so the rate of change of dy dx is the derivative of that. So if del x, if the derivative of dy dx if the derivative, so this is your dy dx, and this is the rate of change of that. So if d dx of dy dx is equal to the rate of change with respect to time of the velocity, so here's your velocity, and I'm going to take the time rate of change of that. If these are equal with some sort of constant, let's call it c for the moment, capital C, then this is a wave. All right. But it just so happens that the constant is equal to 1 over the velocity squared. Okay? So if your equation, or if your function satisfies this equation, then your equation is a wave. And we write this as the second derivative of y with respect to x, partial, is equal to 1 over v squared with the second derivative of y with respect to time. Okay? So let's apply this equation to our wave that we've been working with. Okay? So the idea is, if I take the second derivative of y with respect to x, I should get back 1 over the velocity squared times the partial of my equation with respect to time, the second order differential of that. Okay? So let's just crank through these derivatives. So dy dx. So I take the derivative with respect to x and hold everything else constant. So this becomes a cosine kx minus omega t times k, because the derivative inside kx minus omega t with respect to x, omega t is constant, so the derivative of that is 0. Derivative of kx is just k. So this equals ak cosine kx minus omega t. And the second derivative of this is a times k. Derivative of cosine is negative sine kx minus omega t. And once again, I get a k out front, or I get a k, and if we pull it out front, it becomes negative a times k squared times sine of kx minus omega t. So what about dy dt? So the partial with respect to t is a times cosine kx minus omega t times minus omega. Okay. Whoops, this is cosine. I missed the cosine. I knew something didn't look right. Okay. And if I take the second derivative of this with respect to time, we get negative a omega. Derivative of cosine is negative sine, so the negative sign cancels out with this. But we get another negative omega, So this equals negative a omega squared sine kx minus omega t. And if you notice, I mean, we just did this in the previous slide, right? Oh, not the previous slide, but the couple before that, right? So the right-hand side of the wave equation is just your acceleration times the square of your velocity. So now we look at these and we ask ourselves, negative a k squared times sine of kx minus omega t is equal to 1 over v squared times negative a omega squared sine kx minus omega t. Okay? And first things first, I can cancel a lot of things out. So right off the bat, I can get rid of the signs. And my a's go away. And the negative signs as well. And so that leaves us with k squared is equal to 1 over v squared times omega squared. But remember, earlier we defined v as omega over k. So v squared must equal omega squared over k squared. And if I solve this equation, v squared equals omega squared over k squared. So this result was from the derivation from the wave equation, and this result was from the fundamental idea that velocity is equal to wavelength times frequency. And so, as a result, we can see that the wave equation, this equation is satisfied by our equation for y. Okay, so this is a really, really important result. And in the next video, we will start to look at waves on string and resonance. All right, so stay tuned.